Okay. So today is about this lecture is about this paper quiver. Okay. Algebras. Okay. From Floer homology and Coulomb branches. And basically, what I will try and explain to you is how to go from some description. So yesterday I explained how to make a big chart in this Coulomb branch, which looks like there's this M, this Coulomb branch. M. And we had this tilde version where we took the while group cover and that's not the tilde version. We had this T O cross T check mod the while group. And this, we yesterday described how to make a big chart like this. And we explained, so last time. And how to count curves in here, basically by counting first the curves in here and then discussing which ones extend to here. Okay, that's what we did last time. So you can forget all of that for now. We'll come back to it in a bit, but first I'm going to kind of gently introduce how we convert some thinking about the Fukaya category into some kind of diagrammatics. So let's begin with the Fukaya category of C star, and this is relevant to this discussion because some part of this story will look like just T mod W, and in the very simplest instance, when the quiver has one node labeled 1, then there's no W, T is C star, and so this is how relevant. But maybe never mind that. Let's just discuss about this thing. So C star I'm going to draw as like this. So this is maybe 0, this is infinity. Identify these two sides. As I explained to you last time, the kind of typical objects in this category look like this. So here's one object, and here's another object. And the typical morphisms between them, last time I said that in this kind of wrapped Fukaya category, the way you would discuss morphisms between this guy and this guy is you would wrap this guy, and so it kind of would start looking like this. Okay, and then you look at intersection points. But an easier way to think about that, or a different way to think about that, is instead of actually wrapping it, we can identify the intersection. We can identify the Halm spaces with trajectories like this. So this is a map. If I go around twice, that's a map, and so on. Okay, so that's the same as these kind of intersection points. And similarly, I can go around in this direction. And so I want to we discussed last time that kind of Halm between. You see immediately from this picture that Halm between this kind of yellow one and the red one is a direct sum over all kind of integers of a vector space, kind of one-dimensional vector space labeled by this guy. Which kind of compose in the way that in some kind of obvious way. So I want to encode that. So encode diagrammatically as follows. So I'm going to draw now another cylinder, but this cylinder has nothing to do with this cylinder. Okay, so objects. So objects. These kind of straight line objects, I'm going to draw them as points. Okay. So those this object and this object will be this point and this point. But let me draw. So an object will be one point on the circle. So an object. Maybe it's better to say it this way. So the map really goes. I say encode diagrammatically, but really the map goes this way. And I take a point on the circle that goes to the cotangent fiber at that point. Okay, so that's. And now I want to describe how to about morphisms. So morphisms, we. Now I've drawn one object of the category at the top and one object of the category at the bottom. And if I have any kind of path some path, I want to associate that to a morphism. And the way I'll associate it to a morphism is let me kind of pull it straight, and then it kind of winds around in one direction or the other. And if it's winding around as I go down, if it's winding around positively, I'll associate it to one of these morphisms. And if it had been going around the other way, I would associate it to one of these morphisms. Okay? So this, or in other words, this path is the time, the movie of the wrapping, defining kind of at infinity, defining the morphism. Okay, and I regard paths as being the same. I consider them only up to homotopy. Fine. And then the last thing I want to say is composition of morph. So I'm defining diagrammatically a category here. The objects of this category are points on the circle. Morphisms of this category are paths in the cylinder. And composition is you stack one cylinder on top of another one. Composition of morphisms. Stack cylinders. So the kind of if you believe our discussion about the Fukaya category of C star from yesterday, this kind of map is an equivalence of categories. Okay. I sent objects, so I defined a category here. The objects of the category were points on the circle. Morphisms of the category were kind of these paths. Composition was composed paths. And so I say where the objects go, I say where the morphisms go, and to check that this is an equivalence of categories, you need to know how morphisms compose here. I told you yesterday how they compose, and so it's an equivalence. Are there any questions about this? This is the simplest example. I'm going to start now making more and more complicated examples like this. So if we're not on the same page here, we should get on the same page here. Okay, good. So the next thing I want to discuss is, okay, not so much more complicated. Let's discuss the Fukai category of C star times C star. Okay, so now I can represent objects. I mean, some objects as kind of products of Lagrange's, one in each factor. And so I'll just draw one cylinder, but I'll use two colors, let's say green and blue. No, let me not do that. Maybe a. So to draw an object, I should draw two Lagrangians. And these two Lagrangians, I'm only use cotangent fibers, but I have to label them. One in the first copy and one in the second copy. Okay, so this is how I would give an object of this Fukai category. The object would be take this one times that one. And if I want to discuss morphisms, so let's have another kind of couple of objects, another object. So again, I label them. Let's say 1. I don't have to label them in the same order. 2, 1. And when I ask what are HOMs between these two objects, well, it's a product of a HOM between these and a HOM between those. So in fact, HOM between this green and this blue, there's one element. I mean, there's one intersection point of those two things. And that's when the 2's intersect times when the 1's intersect. Okay? So there's this kind of HOM, green, blue. So now I'm not wrapping. I'm just taking these literal ones. So and not wrapped yet is just one dimensional. And so I'm going to have some kind of this diagrammatics encoding. And the way I would encode this is that I have the green guy. I guess since I moved the blue one, maybe it's easier to view this as a morphism from the whatever. So I have the green one, and then I have the, and I label them 1, 2. I have the blue one. I label them 2, 1. And it doesn't matter. I mean, like the and if I were to kind of draw if I were to kind of try and draw some such diagrammatics, it would look like this. Okay. And of course, I forgot to say one thing about this composition rule, which is that, I guess maybe I said it, which is that you compose them, but it's only up to homotopy, so you can pull it straight afterwards. And now pulling things straight here, there's certain question arises, which is what are you allowed to do if I have this kind of situation that's 1, 2, 2, 1, 1, 2. What is this composition? Okay, and I mean, if you think about it, here the two factors had nothing to do with each other. So these kind of two different strands, they don't really interact in any way whatsoever. This. Okay, so if I wanted to kind of diagrammatically describe, I mean, it's ridiculous to draw these, in some ways it's ridiculous to draw these diagrams, no one would ever do it because this is an extraordinarily simple category. This thing is, you know, it's modules over C, T, plus minus, S, plus minus. And so it's like two copies of the thing. I mean, maybe it would have been better to write this as C, T plus minus tensor. It's just like, you know, Fukaya category satisfies, it splits over products into tensor products. But if I were to draw this kind of diagrammatics, which is going to evolve now into this KLRW diagrammatics, this would be the kind of rules. Any questions about this this diagram? Okay. Yeah. I mean, Fukaya category is a category of, it's a category, and
so I mean, what is the equivalent to what kind of module there?
oh, it depends what you mean by this. If you mean the usual thing by this, maybe I should have written perf. But it just depends what you mean, you know, like when you write Fukaya category, like in the old days, people meant things actually, you had actual Lagrangians, and then maybe you take the triangulated envelope, and then maybe you take the idempotent completion, and then maybe you take the ind completion. Okay, so depending on which of these moves you feel like doing, you have to write different things on the other side. And so I think maybe the most conventional thing is to take the triangulated completion, and then I would write perf. Okay. Good. Now, now let's do a more interesting example. I'm going to think about sim to C star. And okay, this is an aside, but so in fact, sim to C star is isomorphic to C times C star. Because what is sim2 C star? This sits inside sim2. This is kind of an irrelevant aside, but I just explain it anyway. It sits inside here, and what is this? This is P2, and how do you describe this? You describe this by writing the equation which cuts out the 2 points in P1. So this thing is a x squared plus b xy plus cy squared. It's like equations like this. And this inside here is the ones where x equals 0 and y equals 0 are not solutions. So this thing is the locus where a, c are not 0. And if a and c are not 0, we can set one of them to 1. And so we're in c times c, and the other one's not 0, so we're in c times c star. Okay, so, and the point of that discussion was to explain that if I were to actually compute the wrapped Fukaya category of this, I would get 0 because we have a c factor. So I'm not going to do that. I'm not going to, so this, when I discuss this, I'm not going to wrap all the way. I'm just going to wrap a little bit and kind of illustrate you some disks which would appear. Or in other words, maybe you can imagine I've put some stops somewhere that I haven't told you about. But let me draw the kind of picture which will be relevant. Okay, so again, I'm going to draw them like this. So maybe 0, infinity. And so how do I draw Lagrangian in sim2 C star? Well, I can draw two Lagrangians in C star as long as they don't intersect. I want to take their product and then project it, and that would be kind of a problem if they intersected. But if not, then it's okay. So here's an example. So here. And I'm going to label them. The labeling means nothing in sim2 C star because I'm taking the quotient by interchanging them. However, it is meaningful when I think about wrapping this guy a little bit. So if I take this one and I wrap it a small amount, even inside sim2 C star, then kind of locally it remembers which one was which, because like how to say. An intersection between these two guys in sim2 C star is the image of an intersection in C times C star squared, right? So okay, good. Anyway, don't think too carefully about it. Okay, so there's this one, and then let's wrap it even more. Okay, and so I want to discuss two different kinds of compositions. So here I'm going to draw the same picture again. Okay. And one composition I would like to discuss is I would like to compose, so again, a morphism between these guys. So now there are two morphisms. Yeah, okay, maybe I should have said this first. So before, when we had the kind of usual product, there was one morphism between the yellow and the green. Now there are two morphisms. I can either choose the intersection where 1 meets 1 prime and 2 meets 2 prime, and that's one option. Or I could have chosen the intersection where 1 meets 2 prime and 2 meets 1 prime. Okay, so there's a two-dimensional space of intersections between these two. I want to, first here I want to draw the kind of naive composition. I want to draw one composition. So I'm going to compose as 1 prime 1, 2 prime 2, with the analogous thing here, where 1 meets 1 prime, and 1 prime meets 1 prime prime, and 2 prime meets 2 prime prime. Okay? Here I want to do the other thing, where I compose with the other one. I want to compose with this one. Okay, so now let's look. If I want to count disks here, there are two kinds of disks in principle I could count. One kind of disk, so what does a disk look like? It's in this kind of cylindrical model discussion, it's something which is a double cover. I choose a double cover of a disk, and I map that double cover to this picture. Okay, and there are two ways to double cover a disk. With the kind of downstairs I'll have a disk with 3 marked points, and upstairs I'll have either I can take a disconnected double cover, where I have 3 marked points on each one, or I can take something with 6 marked points on it, which is a branch double cover. Those are the two ways to double cover a disk. And I'll leave you to think for yourself that there are no maps from this one to this picture. But there are maps from this one, and those are the following. So there's this triangle, and this triangle. And by contrast, on this picture, there's kind of this big triangle and this small triangle. Okay, so that's that's how you would compute these compositions in this symmetric product. And there's one important thing to pay attention to about these compositions, which is that let us think about whether the disk passes through the diagonal of Sim2C or not. Okay, so and what does it mean that the underlying disk passes through the diagonal? It means that I should find kind of a point on the base disk whose 2 preimages map to the same point in this picture. And it's clear here that can't happen. One of these things is a translate of the other one, so no point in one is not, it avoids the diagonal. So here the disk avoids diagonal. And here On the other hand, I have this outer one and the inner one, and there's some fact in mathematics called like the Brouwer's fixed point theorem or something, which tells you that if I have a disk and I map it inside of itself, there's one point, at least one point is fixed. Okay, which says that this guy meets the diagonal. Because this thing was a double cover of the disk, and the two pieces that map here and here, and so there's one point at least which maps to the same point. Fixed point theorem implies that this disk meets the diagonal. Okay? So in particular, if instead of thinking about sim2c star, I was thinking about sim2, so in sim2c star minus the diagonal, this disk does not exist. None of this disk. But this disk does. So now, if I were to do the diagrammatics, if I was going to try and make some kind of diagrammatics for sim2c star minus the diagonal, I would have the following rule. Maybe I'll do separately, both sim2c star and sim2c star minus the diagonal. sim2c star.
Can I ask you?
Yeah.
This picture is one peak, one star, one peak, one pi, two peak, one pi.
Sorry, what?
Intersection. This is 1 peak, 2 pi, 2 peak, 1 pi for both intersections, right? Okay, you have one of these and
slowly. There were too many words.
That's two intersections, one here, or two, right?
One and two.
And the other one has 1 and 2.
1 and 2.
Yeah, and you take one from the left and one from the right.
Yeah, you could also consider that and ask what would happen. Yeah.
They also have this, right?
Yeah, they also have this. If you take one from the left and one, it'll look more like this picture. So let's just do it. So if I instead had this one, let's say, and this one, then you can see the disks. It'll be like here. And here. And the point is that what this tells you, which should not be a surprise, is that the thing that sends 1 to 1 prime and 2 to 2 prime is the identity. So if you hit it to anyone else, then there should be a disk. Yeah, so the diagrammatics for sim2c would look like this. So if I had this kind of green and this blue, then these two different kinds of morphisms I was discussing, one of them is just these kind of lines traveling in a straight way. So this is okay, let's undestroy this picture. Here we had this. Okay, and the original thing I had drawn here was I had this 1, 1 prime, and 2, 2 prime. So this kind of map is the kind of map I drew here, except I guess I called them yellow here. Okay, and then I had this blue thing here. And so what this calculation shows you, what this discount shows you is that here this composition equals, just forget this middle thing. So this discount, which I just did, justifies the following diagrammatic rule. Okay. Because it says that the composition of this one and this one is this one, and that's what this says. And on the other hand, if I look at the other kind of composition, here, that one, so again, the picture's like this. I know this was yellow. Blue, green. And now this, the rule for drawing the picture, remember, is that I connect the green strand, the dot corresponding to the given green strand. I draw a path explaining how it got to the corresponding yellow strand. And the green strand has gotten to the gone to the opposite one of the yellow strands. So this intersection, my diagrammatic rules, which I explained earlier, tell you to draw these paths. Okay, and then again, the same for these. So, and now this discussion here says that this in sim to C star, this composition should be this one. Okay, and in sim to C star minus diagonal, it's 0. Okay, so that's the discussion so far. All right, now let's go back to this scalar W stuff. But hopefully you already start to see where these scalar W kind of pictures are going to come from. Okay, so this kind of KL relations. Actually, before I get to the KLW relations, let me say one more thing. Maybe I'll say it. Maybe I'll write the KLW relations and then I'll say it. So the scalar W relations. So I'll just write the ones. So the quiver I'll restrict attention to this for this lecture, this discussion. And so this kind of KLRW relations are the following. This is 0. So that should be now familiar. This is like this. This like this, and I keep a variable here, and this minus this is like this. And all other braid relations and bygone canceling. I guess there's no other bygone canceling in this case. So when I say all other braid relations hold, there's a braid relation which involves 3 white strands. And the statement is I can freely move it over to the side. Yeah. Okay, so fine. And so how to prove this kind of KLRW maps to this Fukaya category of this Coulomb branch. M, G. I have to again tell you about objects, morphisms, and compositions. And a given so let's just get started. So objects. An object here is a circle. Okay, I'll just draw it as a straight line. Connect the ends as you want, and some white dots and some red dots. Okay. And this object, I send it to this picture. So there's some, as I mentioned in my lecture in this conference, and I didn't explain in so much detail last time, there was some superpotential function W on this space. And this function, it depends on some points in C star. So I draw that here. Okay, about morphisms. A typical morphism here maybe looks, I guess there's 3 kinds of morphisms here. 3 like generating kinds of morphisms. Here is one kind. Um, there is another kind. And the third kind is like this. I draw a dot somewhere. And I forgot to tell you that this is times its extra factor. This one?
Yeah.
What about it?
Yeah. That is a singular.
Let's discuss this red dot. So that has to do with this deformed business. So last time I explained that there's this Coulomb branch. So we had this. Remember, so I'll draw in this case of this kind of this quiver. Remember, we took this framing node of this quiver, and we had this torus acting. So this has some rank, some mi, and I forget which one I call which. Maybe I call these di and mi, and there's a torus acting here, C star to the mi, and I fixed some weight of it. So I fixed. So we fixed beta in this C star. I guess there's no I, so there's just D and M. And C star to the M, and we write it as beta equals beta 1 beta M. And that trivialization, so this, we had this kind of, this M tilde beta over T mod W. This M beta over T mod W. Okay, let's put the tilde like this. And then there was this thing. If I take this one, so inside here, there's T minus various hyperplanes. And in this case, there's two kinds of hyperplanes. There's the hyperplane. So okay, this T is now it's C star to the D. So this is T minus this kind of root hyperplanes minus one of the coordinates, one coordinate is one of the beta I. Okay, so over this locus is where over this locus, this M tilde beta restricted to this this locus. This is the one which was trivialized. So let's call this thing T sub O, T O. This is the thing which was we had some trivialization as T O times T check. And this red dots are recording the location of these beta, the values of these beta I.
Why is it an object? Why the object?
This, maybe I should have began this sentence by saying fix beta. And fixing beta, and I fix beta as so that the arguments of the beta I are all different. Okay? And I put these red points, I mean this is a circle, and I put the red points at the locations of the arguments of beta I. And so those red points are fixed throughout. And when I draw a picture here, I'm trying to give you a Lagrangian, first of all, living in TO times T check. And for it to live in TO, I have to avoid wherever these beta i's were. And I should say also, I didn't emphasize about the superpotential yesterday, but I should say also that the nature of this trivialization is that this potential function, whatever it is given just by the sum of the coordinate functions on T check. Okay, so this is a key aspect which I didn't emphasize yesterday. So this potential W restricted to this TO plus T check equals sum of coordinates on T check. Yeah, so in particular, this trivialization depends on beta. It won't, yeah, okay. So the relevance of this fact is that when I think about what the prescription is for wrapping such a Lagrangian, the potential function only has to do with the fiber, so it means that I wrap in the base as usual, and I wrap in the fiber as if there's a stop here. Okay, because like it's just the function z on this guy. Great, so that's what I do with objects. And then, yeah, what about morphisms? So for each one of these three morphisms, I should tell you where it goes. Because these generate this thing. And so, very good, I'll tell you. So to tell you, I need to draw a kind of another copy of this object, and then I'm allowed to wrap it. So let's do that. I'll wrap it. Take another copy of this guy and wrap it. Okay. This morphism goes to the kind of morphism which mixes the pieces of this one. So it's like this one originally corresponded to this one, so I take this morphism. Okay, so that's the same condition. I mean, that's the same description in this diagrammatics that I used for this sim2 C star that I just discussed previously. So that's where this morphism goes. What about this morphism? Oh, I should say what, I need to tell you the intersection points here and also here. Here, I kind of wrap them a little bit, and I take the kind of identity intersection points, so these ones. Okay. That's for this morphism. And then what about this morphism? I'll only draw on the base, because I'm going to, again, take the identity intersection points in the fiber. And so we have this object. And the other object now is a different object. It's kind of this same one, and I'll wrap it a little bit. It's now one that lives here. And so it begins life kind of looking like this. Okay, but I'll wrap them also. And it's this intersection point. Okay, so that's where I send this morphism. And then this last one So this goes here. And this last one goes to the identity in the base. And in the fiber, I have these three, and I take the following thing. I now have to wrap it a bit more. Okay, and with this wrapping, there'll be some person who is the representative of the identity. It's hard to tell you from just this picture which one it is, but it depends on how you set up all the things. Let's say that the thing in this picture, which in the limit of wrapping represents the identity, was this picture, was this guy, could be, okay? Then what that morphism gets sent to is the thing where on the second strand I use the next one. Okay, so it's saying that I kind of use the identity copy on the undecorated ones, and one dot means I wrap one extra time on the decorated one. Okay, so this is the prescription for where the morphisms go.
So those spots refer to the fiber, right?
Yeah, the dot's the fiber wrapping. Yeah.
How many times you wrap?
How many times you wrap in the fiber? Okay, so that's about the object.
Stop there, so you can wrap it one by one.
Yes. Oh yes, I forgot to put the stop. The way I did things, I should have put the stop maybe on this side. Because if I'm to say that these are the identity ones, they should be the ones that are closer to the stop. Okay. Yeah, great. So okay, that's the story about objects and morphisms. And now I basically have to convince you that that the compositions work out correctly, right? That's what's left. There's a little bit more. I have to convince you that I get all the morphisms over there. But that's a matter of just like counting the intersection points or something. But the real content of whatever argument there is counting the disks for these morphisms. Should I take a break now and then continue it in the next half? Okay, yeah. So I'll do the discounting in the next half. Okay. Yes, in the last hour, we explained what is the meaning of these pictures. Somehow from the diagrams which are a line with some dots on it, you could produce Lagrangians. From this kind of diagrams, which are these kind of KLRW diagrams, you can produce morphisms. And what remains is to discuss whether this kind of KLRW composition rules match up with some discounting. Okay, that's the what's left, and that's of course the most contentful part. So yeah, let's look at these various rules. This one we discussed a bit already. So we saw that in the symmetric power minus the diagonal, the analogous thing would be 0. Okay, now in our setting now we have the diagonal. However, there is a rule about whenever you cross the diagonal, your disks have to have some poles or something, right? You remember this rule I wrote about how to do disk counts. So I wrote this rule like two or three times ago, which says that maps from a disk to the Coulomb branch are, you describe them by first taking maps to the symmetric product, which is at the base. You reinterpret that as a map from the cover of your curve to C star. And to extend over these divisors, you're allowed to do it if some condition. And that condition was when the condition for extending over the root divisor, the one that corresponds to the diagonal in the symmetric product, was that your covering disk had to have, I forget, a 0 or a pole there. But if you remember the diagrams which we drew that were computing this guy, none of those disks went to infinity in either direction. They were in finite space. Okay, so those don't extend, and so we get 0. So this relation holds by the discussion we had for the symmetric product at the beginning, earlier in last lecture, plus this kind of business about the rule for lifting things to the Coulomb branch. Okay, what about all these other pictures? So let's discuss this one. So that okay, so we want to think about this. And what does that correspond to in terms of some actual Lagrangians? Well, inside this kind of base copy of C star, we have a picture like this. Let's use some colors. I'm going to get the colors wrong if I try and use them. So we have, so 3 Lagrangians. And why these 3? Well, I begin on one side of the x. So I have 2 of them sitting on one side of the x, and one of them sitting on the other side of the x. Okay, I should have drawn this the other way then. Let's have this. So this picture here should be a morphism between a Lagrangian which begins life to the left or right of the x, and a Lagrangian that begins life on the left of the x. So maybe it's this intersection point. And this one is in the other direction. So maybe it's this intersection point. What have I done here? Yeah, I think maybe in my notes I've labeled it incorrectly. So this is maybe this intersection point. And then we have here. Yeah.
That one white line would look like each of them one.
This one?
Yeah,
I mean, how to say it? Let me. So. This will be maybe clearer. So this picture is a morphism between what should be a Lagrangian that I'll color in orange and one I'll color in green. And so the one that I color in orange should be to the right of this red x. So it's this one. And the one I color in green should be to the left of this x. So this one. And then this picture, it should be a morphism between this green one and some blue one, which is this blue one. And so then I want to compose them and then learn something about a morphism between the orange and the blue one, which it probably is here. Okay, but I should also discuss the, I guess maybe before I discuss anything, what I cannot do is take, so you might ask, could this possibly be, could there be a disk in this count which is kind of the straight line? And the answer to that is definitely no, because the downstairs disk, what would this mean? This would mean that kind of upstairs I had this kind of picture. So this is not the correct picture, so I'll erase it in a second. But this equality would mean that upstairs I had this picture. Blue. And I would count this disk. Okay, that's what would correspond to such an equality, because it would say that, I mean, if this were a legitimate disk, then I would learn this. And the reason this is not a legitimate disk is because of this disk lifting rule, which says that if this disk passes through this kind of x point here, then it has to go off to 0 in this picture. And this one does not. It stays in kind of this finite region. Okay, so this is not a disk. So this. But maybe let me draw the one which does exist.
That two big equal, the base is not the same configuration, right? The base.
Sorry, what?
So you draw that base picture, right? That corresponds to the picture on the left.
This?
Yeah, that. But this one is not that picture.
So yeah, this is, yeah, let's just discuss what is this. This is this intersection times this intersection. Okay, that's what that picture would be. Yeah, maybe if I draw it. And so if that disk had existed, and no other disks had existed, then these would be equal. But this disk lifting rule tells you, in fact, that this does not exist. So this. Okay, so now let me draw what is supposed to be true. This kind of one of them is this kind of wrapping. Okay, and which one is which? I think I unfortunately did not color them in my notes, but I guess it better be like this. Okay, so, and the statement is that I use this kind of standard intersection point between these two and the standard intersection point between these two, and the disk which exists looks like this. Oh, no. No, stop going here. No, yeah. There we go. Okay, so it has these three corners. It has one convex corner and two concave corners. And it has a kind of a puncture out in here. And because it has two concave corners, the moduli space of such configurations is two real dimensional, and those two dimensions cancel with the condition that you have to have this particular complex structure of disk. So this picture tells you where this kind of central point goes. So anyway, this is the disk. So this, so if you think about it and count dimensions and so on, there's one disk like this. Actually, I looked back in our paper, and I think we didn't carefully compute the sign. So in principle, one should compute the sign of this disk. But what does this disk say? Well, it says that if we compose this intersection between the orange and the green with this intersection between the green and the blue, we get this intersection between the orange and the blue. And this intersection is the one that's one dot. Because, I mean, this would be the kind of identity one, but I've had to go around one extra time. Okay, so this says that what this composition actually is this. And I put this parameter here because it's convenient in the actual argument to keep track of how many times you intersect these two different divisors. And so we intersected that divisor once. You can set these parameters to 1. It's not really relevant. Okay, so that explains more or less this relation. Okay. Now, what about this one? This one is really hard, actually. I'm not going to try and give the full proof of this relation. It takes like 10, 15 pages in our paper. I mean, again, it's some discount. And it's this discount. So what are you supposed to do? Well, you're supposed to compose some kind of map with a dot together with this kind of crossing. And well, the map with a dot is, so the map with a dot's between the blue and the green. So I take the blue and the green, and I take the morphism, which looks like the identity morphism, which is this one, not the other one. And then I, on top and up here, upstairs, to get the thing which is the dot. The reason it's so complicated is now it's something about two Lagrangians, so it's, you have to drop. So then I take upstairs, I take the kind of morphism, which with a dot, which means it's kind of not this first one, but this kind of second one. Okay, so here, and yes. So I take, and I only have a dot on one of them. So I take the morphism, which is kind of, a morphism is a pair of intersection points. And so I take the one that's kind of trivial for one of them and wrapped once for the other one. Okay, so this morphism corresponds to one dot. And then I compose it with a morphism that's the x. And what is the morphism that's the x? That's the thing with the orange intersects the green and intersects it as soon as possible close to the stop, so it should live here. And it should be the one which mixes up which one is which, so the kind of outside one should pair, the one that's further away from the stop should pair with the one that's closer to the stop. So I take this one, and vice versa, so I take this one. So that's why we have these two pointers here. Okay, so I should compose this with the other thing which I said, which was this. Okay, so we're trying to do that composition, and we want to know what is the result. And what this discount is this is about the question of whether or not this element, this kind of identity element, appears in the result. And what it would mean for this to appear in the, what it would mean for this to appear is basically this picture, that such a disk exists. That's what it would mean. However, if that were true, it would just say that this equals this, not this difference.
And the H bar refers to?
The H bar is counting how many times you intersect this root divisor. And the fact that you intersect the root divisor is the fact that here this disk is a branch double cover. And that has to be a branch double, to have this picture, it has to be branched somewhere, and at the point it branches, you intersect the root divisor. Yes. So if there were always such a disk and exactly one, it would say this formula was true. But the actual situation is that one can show that so the way you show this is you study some moduli space of which the boundary consists of configurations that correspond to these three pictures. So what you can actually show is that kind of either you can show that either you have like the difference between the amount of disks like this and the amount of disks like that is one. That's what you can actually show. But it's not an easy argument. It's some kind of the nature of this calculation is some version of this argument I gave yesterday, but kind of a much more elaborate version.
Is it easy to see there's no other piece?
Yeah, so one's life is made easier in this regard by some gradings I haven't told you about. Some gradings. So this space, this Coulomb branch has a lot of topology, and for every kind of H1 class, you can put a grading. And when you use all those gradings, you can eliminate all but a very small number of possible places where a disk could live. Yeah. Okay. So that's if I run out of things to say tomorrow, maybe I could give this argument. But it's a long argument. I don't want to give it now. So that's about this relation, and finally this relation. Actually, it turns out that these two relations together imply this relation. Yeah, so this one and these two together imply this one. That's an elementary fact by manipulating diagrams. That these two imply this. Okay, so that's basically it. That's how you prove this thing. You count this disk, you count that disk, and that's it. That's the proof. So maybe I'll state a theorem. theorem. And this is due to, this is in this paper with Aganagic, Danilenko, Yishuan Li, myself, and Peng Zhou. And the theorem is that there exists a fully faithful embedding in this KLRW category into, let's put the quiver Q into this Coulomb branch. I guess I should put the quiver Q. Okay, fix beta and C star the appropriate dimension vector, fully faithful embedding from KLR and with distinct arguments. Q, we should put kind of the dimension vector, this kind of this arguments of beta. So these are these kind of red points. This tells you how many of the white points that there are. And this thing embeds into the Fukai category of, we take this kind of Coulomb branch for this quiver Q, deformed by beta. Well, I guess you can either put the beta in the deformation or you can put it in the potential. So I'll put it in the potential. That's the statement. There exists this embedding. Yeah. Sure. I mean, how to say it? There's nothing A infinity about this guy. So part of the theorem is that the image, like, yeah, on the image of this thing, the A infinity structure is kind of stupid. But that's true kind of for this kind of grading reasons. It's not, there's nothing kind of subtle about this aspect. And some kind of aside, so there's a theorem. Sorry. I forgot one of the hypotheses. This is true whenever this Coulomb branch for Q is smooth. And this is true, so at least when Q is ABE Dinkin. I don't actually know what is the, yeah, I don't know when this is true in general. So, I wrote last time that, okay, I didn't write last, I don't know if I wrote it not. So the original definition of this was, the following two things are the same. Either I can do this deformed version and delete this one divisor, which I wrote last time, or I can just take this. Those two things are equal. So just smooth. The thing which is not, I mean, this Q is the original quiver, not the quiver with all these extra, not this kind of framed quiver. The thing which you deform is this framed one, right? So, yeah. So I just mean this statement as stated. But you can.
So this is the spectrum of this algebra.
Yeah. This discussion about deformation is relevant to write this function. Okay. Yes, so that's that theorem. Oh yes, I was going to say, so there's a theorem of Ben-Webster which says that this kind of KLRW is coherent sheaves on the additive Coulomb branch. Okay, so if you put these statements together, you get some kind of mirror symmetry. We expect this embedding is an equivalence. The reason we have not proven this embedding is an equivalence is that, so it's known that the Fukaya-Seidel category for a Lefschetz vibration is generated by thimbles, assuming that the potential function has no singularities at infinity. But this function does have singularities at infinity, so we can't just literally apply that result. So what I expect is true, and what I think some people have claimed, some people are trying to prove, is that what should be true is that when you have a potential with some kind of Morse singularities at infinity, there's a notion of thimble to infinity, which is you just ask like who under the usual thimble flow flows up to that singularity infinity. That should be again a disk if that singularity infinity is Morse, and the kind of thimbles plus these kind of thimbles to infinity should generate. I think maybe many people have this expectation, but so I think maybe some student of Scheele and some other people are trying to prove that or have proven it or something, but I don't know if this potential is Morse at infinity. I'm not even 100% sure that there's what the proper notion of Morse at infinity is. Okay, so now I want to say a little bit about Kavanagh homology. I won't say too much about it. So Kavanagh homology. I mean, this was kind of the original motivation of Mina for studying these kind of spaces. So there's a theorem of Webster which says that there exists a braid group action on the kind of category of KLRW modules and some distinguished element, some elements, I'll call them cap and W. And so this such that so what Webster's theorem is for any quiver, but let me specialize it to the case where the quiver is one dot. And the braid group, which braid group, so when the quiver is one dot, I'm supposed to put some kind of dimension vector. And so let's put that dimension vector. So I can say it's the braid group on these strands. Okay, so the D strand of braid group acts when you have. No, I said the wrong thing. Sorry. Let me try again. This was. I put the framing here. Yeah. And let me D and it's the braid group on M strands. That's better. That's better. And then the last thing to say is that there's some element, this thing, and this element lives inside KLRW dot, and so whatever this n is, I put n to n. Such that HOM, so if I take this element and I HOM it with some braid, this is braid, I wrote the wrong things here. Again. There's a braid. Times cap WN. And this is the Kavanagh homology of the Platt closure of beta. And Platt closure is the following thing. So I have some braid. On an even number of strands. That's why I had to correct myself down there. The Platt closure means you do this. Okay? This is called Platt closure. So once you know that, this theorem tells you that at least that there's some braid group action on this this Fukai category, so that you can extract Kavanagh homology from it. But that's not so satisfying, because you might want to know that the braid group action comes from geometry in some meaningful way. Let me tell you about that. So we have this kind of pictures. With some x's, okay, and some Lagrangian, and we get a braid group action. Okay, well, let's not put the word braid yet. That's just in general. Given a family of symplectic manifolds where the symplectic form stays in the same cohomology class, X over some base, we get an action of pi1 of the base on the Fukai category of some fiber. Okay, and that's because, well, what's the action? Well, you do symplectic parallel transport of Lagrangians. And this is some kind of variant. So if you have so same for family of potential of kind of pairs. So if I have x to b, and I have a potential function w, and then
So it's a family of synthetic manifold, all those spaces. Or the performance. Unit of class to be constant.
yeah, I need the class to be constant. Yeah, I said it, but I didn't write it. That somehow the cohomology class of the symplectic form is not changing. So same story for a family with a potential as long as kind of there's how to say it? Wait, W is non-singular with respect to phi. Okay. So and non-singular means also non-singular at infinity or whatever. In the case at hand, you'll see kind of geometrically the action explicitly without having to think so carefully about this. But yeah. So so what kind of action should we have on these categories? Well, these categories depended on this choice. And really, I actually wrote the wrong thing here. I should have said it's in C star to the m minus the diagonal. I don't want the kind of betas to collide, right? They're like the different points. Yeah, so in this case, the space of the space of these betas, we get an action of pi 1 sim. In this case, this 2n C star sim 2n C star on this Fukaya category. Okay, like by monodromy of this in this space. And geometrically in these pictures, what this is just moving around the x's. Okay, so you can kind of see what that is doing. So we start moving around these x's, kind of go around, and if I I can follow the Lagrangian along with them, and keep going. Eventually, you get this thing. Okay, so this you can kind of see how this monodromy in the space of this structure induces a kind of a very geometric braiding, a braid group action on these Lagrangians. And okay, well, so now I want to say something about how to compute this action. So maybe I'll just state the theorem first and then say some words about how to prove it, and then theorem, and this is with Elise Lepage. And the theorem is that this kind of monodromy kind of monodromy of potential braid group action equals Webster's action. So Webster's action, well, maybe I'll tell you what Webster's action was. So there I just said there exists, but let me say what it is. So Webster introduces a bimodule. So the nice thing about this kind of this diagrammatics is you can make new structures very easily. So here these kind of red point with white points, and some red points, and Webster introduces a new person we didn't see before, which looks like this. So this was not a morphism in this scalar W. This was not a morphism in the scalar W business. What Webster defines a bimodule. So, and the bimodule is you kind of draw this thing. You draw any kind of arbitrary scalar W type diagram on this side. And you draw any arbitrary scalar W type diagram on this side. Okay, and you take the span of such things, and you quotient by the scalar W relations, and also any kind of braid relation involving this X. Okay, so plus braid relations involving X. So for example, this is the same as this, and all similar relations. So this is some at the moment it's just some linear space, but you can act by the top and the bottom by scalar W diagrams, so it becomes a bimodule. So you get a bimodule. And a bimodule induces, by convolution with it or whatever, gives you a functor from the category of modules over this thing to itself. And this, the definition of the braid group action is that the positive twist, so the strands correspond to the red dots, and the positive twist between two strands is this bimodule. That's the definition. So to show that something, and of course, that defines a bimodule. It doesn't prove that it gives you a braid group action. And then Webster proves with a lot of diagrams that this gives you a braid group action. This thing is obviously a braid group action, just a priori. But the virtue of this Webster argument is that he can then prove that he gets Kavanagh homology, because his diagrammatics are related to all kinds of other representation theory. And so if we want to show that this geometric braid group action can be used to recover Kavanagh homology, which is what we want to show, the main point is to show that it's the same as Webster's braid group action. And so to show that, I should explain to you, and maybe I'm a bit tired so I won't explain too much, how you compute such a thing. So the way you, and what does compute mean? Compute means, so this picture, when I describe the map from this scalar W to this geometric setting, the only things in the image were people with lines went straight up and down. And this is not such a person. So I have to express this in terms of the old people. Okay, so that's basically the job. And I have to do it not just for this guy, but for anyone. So like, I have many and other stuff. I mean, of course, stuff on the outside comes along for the ride, so it's not so interesting about that. But the kind of interesting part is that I have maybe many of this. Okay, so I have to, in general, explain to you what to do with such an object. And so let me just say a few words about it. So there's kind of one basic principle. Maybe I'll just enunciate this basic principle and then. So already in this kind of one strand case, I claim that this object is isomorphic to the code on the following morphisms. So, how to say it? This is a, these are three different Lagrangians. I'm not taking like a Lagrangian in the symmetric power, so I draw them in different colors. And there are morphisms that go this way. Okay, so it's a basic fact of this kind of symplectic geometry that you can resolve such people like this. And let me just say a word about why. Maybe I'll give you two different arguments. This is ancient knowledge. And why is it true? Well, one way to see it is that if you want to understand this, never mind the red x's, they could be anything there. If you want to understand this kind of object, and you want to understand, so how do you understand an object in a category? You test it against all other objects. Okay? And so if I test this object against some other mystery object, so here is some other mystery object. Whatever this green guy is, I can send this white stuff kind of far enough off. I can send it like very far away so that disks can only travel in kind of one direction, because there's kind of a big energy jump here. So this HOM acquires some kind of filtration whose associated graded pieces look like you only interact with these three separately. This is some kind of standard argument of this subject. And what does it mean that as a since as a module it has some kind of filtration whose associated graded is this direct sum, that's exactly the same as saying it's the cone on some morphism. It doesn't tell you which one, so then you have to compute which one. But anyway, so this argument I just kind of very briefly sketched is kind of a, you'll find one version of it in these GPS papers. But there's that's one argument. In this dimension, there's maybe an easier argument, another argument. Well, I don't know if it's easier. So there's some kind of general statement that taking the cone on morphisms is the same as on a morphism, the same as Polterovich surgery. And that statement has a proof which is similar in spirit to this statement, but another way to see that kind of thing is if you take some other kind of mystery Lagrangian and you ask how do disks between this guy and this cone look like? Well, they look like this, which is the same as that disk would look like if you did this. Okay, that's basically the argument. And one thing to say about it is that if I do that surgery, well, I have, if I literally do that surgery, I have this stuff. But these pieces are just 0. I can push them off forever. Or to say it differently, if I have any other Lagrangian, I can isotope this stuff so it never touches that. Okay, so you get rid of these. But that's some kind of argument about why you do this cone. And now let's do the kind of more sophisticated version. What do you do with this thing? What turns out to be true is that by the same argument, you can break them one at a time. Okay, so this object, whatever it is a cone on 2 people, one of which, so you can only do one at a time. One of which uses everything else and this one. And the other one uses everything else and this one. And the morphism is kind of like identity morphisms and all the other components. And this morphism on this guy. Okay, so that's by whatever argument you believe lets you do this breaking in the usual setting. Same argument tells you can do this breaking here, but only one at a time. Of course, you can do it inductively now. Just like break it one at a time and just keep doing it. And if you do that, you get some enormous chain complex for this thing. It's going to have like 3 to the n terms or something, where n is the number of this strands. And that chain complex is much, much bigger, much bigger than whatever Webster's braiding tells you. So there's the main work in this paper with Elise is getting that under control. And the basic fact which lets you control it is the following. So when you start breaking this thing, you will, in this process, maybe I'll just state this fact and then stop. So you will see many people which contain this picture. So like if you start breaking that thing, then eventually you see this thing, and then maybe some map here and so on. Okay, so, and the statement, so the lemma which makes this calculation at all possible is that this equals 0. It is not obvious that this is true. I mean, you will not succeed in looking at this and telling that it's 0. You can prove it's 0 in at least 2 ways. One is you can, so of course by this picture I mean this times the kind of, in this extra copy, some straight lines. You can prove this in 2 ways, at least 2 ways. One is that this one, now you can break at the top. And so you can write it as some explicit cone, like it has like a 4-term resolution. In terms of the objects we know how to write in KLRW. And so you can go to KLRW and just check that that thing is 0. Okay, the explicit calculation. And the other way is you can actually find the disk which shows that the identity is a boundary. So if you take this guy and you like wrap it or whatever, you can draw a disk. So maybe I'll stop there. That's,
So this shows you that it's the same action as well.
Same action, yeah, same action.
And this is the key right now.
This is the, I mean, how to say? I would say that,
The finding that this is similar to what you were.
yeah, similar, yeah. All the arguments are, you always find them the same way. What I would say is that this is what makes it possible to do at all. But once you know this, there's still more work. In fact, maybe what's true is that this thing plus this argument of breaking and so on, that kind of shows you that that the maps do the right things on objects. But then you have to argue that they do the right things on morphisms. And for that, we use some kind of trick. Some trick. I mean, the nature of the trick is that Webster has a braid group action, we have a braid group action. If you do one and then invert the other, you get some kind of automorphism of the category, which fixes some set of objects. And then we prove that there's actually, we prove by algebra that there aren't so many such automorphisms. But yeah, I mean, this is the reason it's possible to do anything at all with this enormous complex is this fact. Because this fact cuts down this complex, most of its terms are just zero.
So when you say the additive is mirror to the multiplicative with a superpotential, so should I think about like I remove some divisor on the additive side which give me the superpotential?
So I think what the belief is that yes, but moreover, the divisor is in these cases, the multiplicative one sits inside the additive one, and the divisor is the complement. So the multiplicative will be self-mirror. I mean, if you remove the potential and you delete this divisor, then you should get self-mirror symmetry of the multiplicative.
Is this concept implied that?
Hmm?
So what you said here implied that the multiplicative one is
So if you knew that the potential came from counting disks through that divisor, then it would imply it. It's not known to me. It might be known to Peng. No, I mean it's not hard. It's how to say it? It's not of a different nature than the things that we already did, because like if we had been doing the additive thing throughout, we were studying Fukai of the additive thing, then it would have corresponded to, instead of having the base be C star, having the base be C. And then going from the additive to the multiplicative means we fix one point in this C star and ask to count somehow how many times the disks pass through that, which is the same kind of thing we've been doing. So probably similar techniques. I think Peng may have told me that he knows how to do it.
So what you're getting is the additive one is multiplicative with potential, right?
So coherent sheaves in the additive guy is Fukai category of multiplicative with a potential.
Switch sign.
If you want to do Fukai category of the additive guy, that's a good question. We know how to do Fukai category of the additive guy, but whether it's equal to this kind of thing that you would expect it to be equal to, I'm not certain.